All right, chapter 1 is done. Now on to chapter 2. Chapter 2 is all about Newton's first law of motion, or the law of inertia. To start this chapter, we're going to look at some of the differences in the thoughts, the reasoning in motion between Aristotle and Galileo. Remember, Aristotle was the Greek philosopher. No experiments. They didn't actually try it, they just talked about it. His idea was that motion occurred in two different ways: natural motion versus unnatural motion. Now, natural motion occurred without a force just being a push or pull. The motions of the sun, the moon, and other celestial bodies that moved continuously without force, those were natural motions. Now on Earth, he said that natural motion was directed up or down, so rocks fall down, smoke rises. He believed all other objects would eventually come to rest. He also felt it was natural for heavy objects to fall faster than light ones, and unnatural motion required forces, a push or pull. So if you wanted to move a cart, you had to push it or pull it. Now, you've got to go along a few years till Galileo comes along, and Galileo actually did some experiments. He decided to test this. Well, one of the things that he tested was to see whether or not objects all fall at the same rate. Now, if you will, imagine for just a minute. Imagine you're sitting in class and I'm holding up two objects, a book and a piece of paper. If I drop them, will they fall at the same rate? Well, you should know that the book is going to hit the desk before the flat piece of paper is. But what if I was to crumple up that piece of paper and then try it again? Would they fall at the same rate? Well, it turns out that Galileo actually did some experiments. Rumor has it, the good story is that he went to the top of the Leaning Tower of Pisa and he dropped two different sized stones. And what he found is that they both hit the ground at right about the same time. So it didn't matter if it was a large object or a small object, they would both hit the ground. They both had the same rate at which they fell. That's if we can ignore air resistance, and we'll talk about that a little bit more. Galileo also talked a lot about inertia. Inertia, he felt, was a tendency of things to remain as they are. So if they're in motion, they want to remain in motion. If they're sitting still, they want to stay still. And so they defined inertia as a property of matter to resist changes in motion. They don't want to move, or they don't want to change what they're currently doing. Status quo type idea. Now, one of the ways that he came up with this idea is to observe what happened to balls. And he would roll a ball and see what happened under different conditions. What he found is that if he rolled it down a slope, the speed would increase. Some force was making it go faster, and we know that force today is gravity. Now, if you take the same ball and you make it go up an incline, well, it slows down. Gravity is still pulling it down. Gravity is acting upon that. That's a force. But if there's no slope, doesn't go up, doesn't go down, it just goes straight horizontal, does the speed change? Well, from experience, you know that it will change. It will eventually slow down. Aristotle would say, well, that's unnatural motion because it's going, it wants to stop. Galileo came back and said, well, wait a minute. If this was on a frictionless surface, that ball would continue going. But because there is friction, there's this little bit of force acting as it's rolling, it is going to slowly and eventually slow down and stop. Now, the smoother and more frictionless surface you can have, the better you can see this particular idea. So if you go to a bowling alley, you'll notice the ball rolls much better than if you would roll a bowling ball across a sidewalk. So that was some of the ideas of Aristotle versus Galileo. Now the next two slides are going to discuss speed versus velocity. Speed is defined as the distance traveled divided by the time. I have the equation up in the corner. By the way, I like equations. For myself, if I see an equation, I can kind of put together what's going on. This particular class is not as mathematically focused as some of my other classes, but you will see some different equations, and yeah, I do expect you to be able to rearrange them. We'll do some things with them throughout the semester. So all you're going to do is take your distance divided by your time. So if you can run 100 meters in 2 seconds, Okay, that would be pretty impossible to do, but let's say you could do that. You would take 100 meters divided by 2 seconds, and you'd end up with 50 meters per second as the speed. You would be really fast. There isn't a difference in instantaneous versus average speed. Instantaneous is the speed at that instant. So if you are in a car and get pulled over by a cop, the cop is watching your instantaneous speed. He doesn't care what the average was when you're driving to town. He only cares about the moment that he was able to use his radar gun and catch you whenever you were speeding. The average is, well, what it says. When you average together all the different speeds at any instant, whenever you're driving to wherever it is you're going, and you average them over the entire time. So down on bottom, I have a problem for you. Yes, you get to do problems in this class. It says, on a trip to Vail, Colorado, we traveled 750 miles in 12 hours. What was our average speed? If you need to, pause presentation for just a minute and try it out. Now, how I would set this up is, well, the first thing I see is we traveled 750 miles. That's my distance. So on my piece of paper, I would actually write distance equals 750 miles, and then time equals 12 hours. Then I'm going to plug it into the equation. Speed equals distance divided by time, which would be 750 miles divided by 12 hours. When you divide that out, you end up with 62.5. What units does that have? Well, in this example, we have miles divided by hours, so miles per hour. You really have to watch the units for the different problems. A lot of times in the class, because we do try to work with the SI system, it'll be meters per second. But in our everyday life, we are a little bit more familiar with miles per hours. So you just have to be careful of the units in the problem that you're looking at. Velocity is determined the same way that speed is. So magnitude-wise, they are identical to one another. But velocity also has to give a direction in which you're traveling. It's considered to be a vector quantity. Vector quantities have to have magnitude and direction. The opposite of that is a scalar quantity. Scalar quantities only need magnitude. So speed is a scalar quantity. Velocity is a vector quantity. Now, if any of you have watched Despicable Me, it's a cute little film. If you haven't, go rent it Friday night or something like that. In there's a supervillain, and he calls himself Vector. And when he introduces himself, he goes, I'm Vector. Vector is a mathematical quantity represented by an arrow with magnitude and direction. And I call myself Vector because I'm committing crimes with both direction and magnitude. And that was after he had stolen a pyramid. So you must have direction, you must have magnitude. Now, if we look at the diagram that's on this particular slide, in this one we have two cars, a red car that travels to the left and a blue car that's traveling to the right. Their velocity is represented using arrows. If you look, those arrows are approximately the same size, meaning that those cars are going about the same speed, but they're pointing in different directions. The red car is pointed to the left because it's moving to the left. The blue car is pointed to the right because it's moving to the right. Also, if you notice, right in front of where it says VC, V just stands for velocity, C is of the car. For the red one, it has a negative out front. And for the blue one, it says positive. Now, in general, and don't ask me why they started it, but this is the way it's generally written, is that if it goes to the right, it's generally thought of as being positive, and if it goes to the left, it's negative. So that's trying to indicate what direction they are going in. And then we have this little person walking at the bottom. Now, the person is moving much slower than the cars. I know that because the arrow is much shorter than the arrows for the cars. It's moving in the same direction as the blue car is going to the right. Now, there's three ways that you can actually change velocity. Now, sit and think about that for a minute. How can you change velocity? Well, the first thing you could do is change the speed. That actually takes up two of them. You can increase the speed, you could decrease the speed, and finally you can change your direction. Those are the three ways to change velocity, and we're going to come back to the same idea of changing velocity whenever we start talking about acceleration. Now we come to Newton's first law of motion. Newton was a scientist. He was actually influenced by the studies of Galileo. So he used a lot of that information, did more research in the area, and came up with these laws. And remember, laws are observations that have been made over and over and over again. Doesn't explain why, it just talks about what they observe. Now, this particular law is also called the law of inertia, and we will talk more about why that is after a while. What this states is that every object continues in a straight line, or continues in its state of rest or in uniform speed in a straight line unless a net force acts upon it. It's worried about the natural state of an object, and remember, this is different than Aristotle. Aristotle felt that all objects would come to a stop unless it was in natural motion, like out in the stars and the planets and all that good stuff. What this is saying is that if an object's at rest, it's going to stay at rest. But if an object is in uniform motion in a straight line, it's going to stay in uniform motion in a straight line unless a force acts upon it. Now, it's difficult to observe an object in constant speed or constant motion on Earth due to friction and to gravity. But imagine, you've seen movie clips or little clips of a spaceship out in space. And they're going along in a straight line, and if they decide they want to change their course, they want to move to the right or to the left, they actually have to fire their booster rockets to be able to do that. So that's one example that I can give of an object in uniform motion, likes to stay in motion. It also says down here, things tend to do what they're already doing. Now the little picture at the bottom shows a gentleman who's doing the magic trick of pulling the tablecloth out from underneath the dishes. And you can see even the candle is standing there. They shake a little bit, but they are all standing upright. That is the example of the first law of motion. So you have a tablecloth, all of the objects are sitting still. All of a sudden you pull on that tablecloth. The objects want to remain still. They don't want to move. And so you can actually remove the tablecloth without disturbing the dishes up on top. Another example of this idea of inertia is if you are trying to swing. To get yourself started swinging, sometimes takes some force to make that happen, but once you start swinging, you will continue swinging until finally friction from your feet or gravity is finally going to slow you down enough to where you stop. Now, for motion to occur, you have to have a net force. Now, force, think of that as just being a push or a pull. Even though a force may act on an object, the force may be balanced. And if it's balanced, there's no motion. But if there's a net force, net push, net pull, one way or another, then yes, there will be a change in motion. And so we can actually see that down the bottom. Now on the bottom I have three different lines. We have applied forces and net forces. On the first one, we have a mass of whatever it is. And then there's these two forces of 5 newtons each. They're both going to the right. So overall, there's a net force of 10 newtons to the right. Newton is just a unit to express the idea of force. We are probably more familiar with pounds. Newton is the SI unit. And we're going to talk more about how that comes about, where they get that idea of a newton in the next chapter. Now the second one, the second mass, I have again two forces. A force of 5 newtons to the right, 5 newtons to the left. Think of that one as being a tug of war. They're balanced, and because there's balance, there's no net force on that object, and so it's motionless. It's not moving anywhere. On the bottom one, I have 10 newtons to the right, 5 newtons to the left. Because 10 is greater than 5, there's a net overall force of 5 newtons to the right. So we can actually look to see what the difference is, the net force. Now if the net force is 0, the object remains at rest. And we saw that on the last slide for the second example where there's 5 newtons to the right and to the left, nothing happened. Now we can express this mathematically by saying sigma F equals 0. And that weird looking E looking thing, that's called sigma. It's a Greek letter. So when you get to big boy school, when you go on to university, you've got to know your Greek alphabet because that's how you're going to get to the right fraternity or sorority for their party. Anyway, so the sum of the forces equals 0. If that happens, the object remains at rest. We call this mechanical equilibrium. Now to give you an example, what we have on the right hand side is a bag of sugar on what's called a tension scale. It's kind of like a fish scale if you've ever tried to see how much a fish weighs. Look and see the force of gravity on that particular mass. So here we have a bag of sugar on this tension scale. The bag of sugar is being pulled downward by gravity. But there's also this upward tension that's holding it up. It's called tension or the stretching force. So these are being balanced because the bag of sugar is being suspended. We have something that is equaling out that gravity to be able to hold it up to where it doesn't fall. If you notice on the scale it says 2 pounds or 9 newtons. Again, don't get hung up about the units just yet. Those are just different units in different systems of measurements. Now on the bottom left, we have some painters working on scaffolding. There's a very interesting essay in your book that's talking about this and how it actually interested the author into physics and into science. So he actually worked on something very similar to this. Now what we have are the lines going up. Those must equal all the weight that's going down, all the forces that are going down. So the mass of the weight of the scaffolding itself plus the weight of those 2 painters. And you can see on the left you have the larger guy who's standing on the very end. The other guy's walking to the left also. So there's more force, more upward tension on the left-hand side than the right-hand side. But remember, they all have to equal one another out. And you can actually do a math problem like this. I believe your book gives some really good examples in the back of the chapter about trying to predict, is it greater than or less than. The support force is something that's going to hold an object up. So if you can imagine, we have an object on a horizontal surface. So we have a book on a desk. Gravity is still pulling that object down, but something's holding the object up. That something is called the support force, the upward force that balances the weight of an object on a surface. It must be equal to the weight of the object. Well, that makes sense. If it was greater than the weight of the object would go flying up. The Earth is pretty smart if you really think about it. It can support us, but it supports us enough that we don't fall into the ground, if we don't sink into the earth, but it doesn't push us up either. So just enough support to balance out the magnitude of our weight. Now the support force is considered to be a normal force. Normal force just means it's perpendicular to the surface. So if the surface is horizontal, then this is going up and down. So let's look at some of these pictures and see what we have. The one on the very bottom compares this idea of support force to a spring. If you press on a spring, you can feel it compress, and it tries to give that example or give that suggestion for the book. The book is actually compressing atoms underneath it. Over on the right, we have a lady stepping on a scale. So her weight's pulling her down. Well, something's keeping her up, and that is the support force. In this case, it's going to tell her how much she weighs. Now remember, if an object is in motion at constant velocity, so it's at a constant speed in a straight line, it is also considered to be at equilibrium. Now we'll call this one dynamic equilibrium because the object's moving. Static equilibrium is if the object's at rest. Static means it's still, and dynamic means that it's constantly moving. So let's go back to this example of objects in motion, and these are at equilibrium. So an object is moving at constant velocity. Example of this is a spaceship, and we talked about how if it wanted to change directions, which would be changing velocity, it would actually have to apply a force. So it actually start its engines up to be able to head one way or another. Another example of this is if I'm pushing a shopping cart at constant velocity, so in a straight line at a constant speed. There is a certain amount of force pulling down on that cart, gravity and friction. Well, I have to push with enough force to overcome that to where it will balance out to form that equilibrium to where the cart will be moving at constant velocity. For many years, people believed that the Earth was the center of the universe and that the sun went around us. One of the reasons for that was this idea of inertia and what's happening all around us. One of the examples they gave is, okay, so if we're standing still, we have a bird up in the tree, the bird's going to drop down to catch a worm that's on the ground. It can drop down. It goes through air to be able to get down, and it can go straight down. But if the Earth is moving, it shouldn't be able to just go straight down. The Earth would actually would start moving, and the bird would get left behind. Now you've seen something kind of like that. If you throw something out the window of a car, so you stick your hand out and you let go of your trash. By the way, don't litter. It's not a good thing to do. The trash does not move forward with the car. It gets left behind. But in that case, we have two different systems. Remember, the law of inertia states that an object in motion wants to remain in motion unless acted upon by a force. So if you were on a plane and you flipped a coin up, straight up, would you be able to catch that coin? Would it come down straight into your hands, or would it move backwards because the plane is moving forward? Well, it turns out in a plane, that's all one system. So as the plane moves forward, all the air inside the cabin is moving forward at that same rate. So if you were to flip a coin in an airplane straight up, it would come down into your hands. It wouldn't bonk you on the head. Same thing as a bird, when it flies down to catch a worm, it only has to go straight down. The Earth is not going to leave it behind because the air molecules are moving with the Earth. Now, this took a long time for people to understand because they didn't travel at high speeds. They didn't understand how it would be. So, next time you take a plane ride, give it a try. Hopefully you won't hit your neighbor with the coin that you're going to flip.